today's section is going to be all about inscribed angles and polygons. And it might be a good idea right away just to describe what an inscribed angle is. So if we're given a circle and we draw an angle within the circle, but the vertex of this angle is on the edge of the circle itself, then this blue angle we just created is going to be called an inscribed angle. So an inscribed angle is an angle whose vertex is on the circle. Furthermore, the sides of the angle form chords within the circle. And remember, a chord is a segment that goes from edge to edge of the circle. So that is what an inscribed angle is. And between the two sides exists an arc called an inscribed arc. And I'm going to highlight that arc now in red. And so that's going to be from A all the way to C. So in red we have our inscribed arc. And in blue we have our inscribed angle. And there's one final piece of information we want, and the endpoints that lie on the side of the inscribed arc are called subtends. And I'm going to highlight subtends now in green. That's going to be that measurement from A to C. So we would say that AC, the segment, subtends angle B, or we can say that AC, the arc, subtends angle B. Alright, so why don't we get into some measurements now? That's mainly what we're concerned about in geometry. So let's look at theorem 10.10. And that is going to be the measurement of an inscribed angle. And if we look at a circle here and we go ahead and draw an inscribed angle, and this is called ABD because our circle name is going to be circle C, we would say that the measurement of angle ADB is equal to 1/2 the measurement of arc AB. So this arc that extends around the inscribed angle, that inscribed arc, is twice as big as the inscribed angle. So why don't we put that to use now in an example? So if we draw ourselves a circle, that's noble. If we draw ourselves a circle here, and we go ahead and go boop to there, and back this way. I'm going to throw some measurements out here. So this inscribed angle is going to be 50 degrees, and this inscribed arc is going to be 48 degrees. It'd be helpful if we had some labels. So we're going to do Q, R, P, T, and S. And we want to find, first, let's try to find the measurement of angle T. So to do that, we have to associate the inscribed arc with angle T and then plug into our formula. So the measure of angle T is going to equal 1/2 the measurement of arc RS, which is, oh, just scrolled up there, which is equal to the measure, or sorry, 1/2 of 48 degrees, or the measurement of angle T is equal to 24 degrees. Next, why don't we try to find the measurement of arc QT? In my notes I said QR, but we can't physically find that. So QT is going to be this arc right here. It is associated with angle R, and we know that the measurement of angle R is equal to 1/2 the measurement of arc QT, or in other words, 2 times 50 degrees, which is the measurement of angle R, is equal to the measurement of arc QT, which is equal to 100 degrees. Doing a little bit more with this, which is going to lead into a theorem. Let's go ahead and look at another circle here. There we go. So here's our circle. We'll put some endpoints. We got S, T, R, and U. And this top angle T is going to have a measurement of 31 degrees with an associated arc of 62 degrees. And this bottom, all right, and so now with this information, we're going to go ahead and find the measurement of angle U. All right, so we know that this is given to be true, right? That is 2 times our inner measurement. And then this arc, angle U right here, is also associated with this 62 degrees. So arc RS associates with angle U. So we know that the measurement of angle U is going to equal 1/2 the measurement of arc RS, which is equal to 1/2 times 62, which is equal to 31 degrees. So if we go ahead and get these arrows out of here, just to clear some things up, this angle is now equal to 31 degrees. Oh, I'm still on the eraser. Notice that these two are equal to one another. And that is actually going to be a theorem that we're going to state. It's going to be theorem 10.11. And it is going to be called the inscribed angles of a circle theorem. And there's a very specific circumstance for this theorem to be true. So if we have an inscribed angle, let's say this is inscribed angle ADB. If we draw another inscribed angle that shares the same two endpoints, so notice that A and B are still the same, we just moved the vertex to now location C, we will know that the measurement of angle ADB is congruent to the measurement of angle ACB. Emily, try refreshing the stream. I am not seeing any dropped frames on my end. Everything's looking smooth. I also have it pulled up on my laptop running off Wi-Fi, so hopefully that's on your end. Let me know if anyone else is having buffering issues. All right, but if we have two circle or inscribed angles that share the same two endpoints, and all we do is move the vertex, then those two angles are going to be congruent. So if we apply that now to an example, we're going to draw this blue angle here, and then we're also going to draw this yellow angle right here. And we know this blue angle has a measurement of 75 degrees, and we want to find the yellow angle measurement. Well, using our theorem that we just did right here, as long as these two are sharing the same two endpoints, which they are, we know that this interior angle has to be 75 degrees. So that's all we're going to mess with inscribed angles for now. Why don't we go ahead and move on to inscribed polygons. And an inscribed polygon is pretty straightforward. If we take our circle here and we draw a polygon inside of it, wait for that to snap, there we go, move it into place, and we're going to make this all pretty, probably just this one time, because as you can see, it takes a bit of time to make it look all pretty. There we go. So now that is an inscribed polygon. So this red circle on the outside is going to be called a circumscribed circle. And this blue pentagon on the inside is going to be known as our inscribed polygon.
Charging battery.
I just heard my cat knock over a glass and break it, so that's lovely. We'll finish the lesson and then I'll go investigate that. So we have this inscribed polygon and this red circumscribed circle, and with that is going to come two theorems, mainly one with right triangles and the other one being with quadrilaterals. So let's first go to right triangles. We'll go to a new page down here. This is going to be theorem 10.12 and is known as the inscribed right triangle theorem. And if we draw a circle and then inscribe within this circle a right triangle, in order for this triangle to be a right triangle, the hypotenuse of the right triangle has to go through the center of the circle. In other words, for a right triangle inscribed in a circle, the hypotenuse is a diameter of the circle. And if we go take a look at theorem 10.13, which is going to be inscribed quadrilaterals, that's a really bad look of quadrilaterals there, isn't that? Anyways, we'll draw a circle here. And we can draw any old quadrilateral we want. So we'll go to here, up to there, over to there, and up to there. So pretty funky quadrilateral. And our endpoints are going to be D, E, F, and G. The opposite angles of a quadrilateral are supplementary if you are inscribed. So we know that the measurement of angle D plus the measurement of angle F is equal to 180 degrees. And then the measurement of angle E plus the measurement of angle G is equal to 180 degrees. And with that, I want to go ahead and do 2 examples. And on both of these examples, I just want to find our unknown variables. All right, so we have this inscribed triangle here. Its hypotenuse is a diameter. And we want to find the value of x. And so while you think about that, we're going to draw another circle here with an inscribed quadrilateral. And this one is equal to y, y, 80 degrees. Doesn't really look 80 degrees, I know. 120 degrees and z degrees. So let's go to this first example at x. The big thing to take away from that is that this side right here is a diameter of the circle because it goes through the center Q. Therefore, a triangle made from the diameter of a circle is always going to be a right triangle. So we know that the measurement of angle B is equal to 90 degrees, and it's also equal to 2x. So we just divide 2 on both sides to get x is equal to 45. Over here on this quadrilateral, we know that opposite angles are supplements. So z plus 80 degrees must equal 180. So z has to equal 100 degrees. And y and 120 must be supplements. So y, we'll say y like that. That's looking bad altogether. So y plus 120 equals 180. Or in other words, y is equal to 60 degrees.